There's a number of different types of reactions for which their molar enthalpies can be calculated using calorimetry. However, only a few will be dealt with in this chapter. Some examples of changes in which enthalpy changes are absorbed are as follows. You have combustion, solution, neutralization, freezing, sublimation, evaporation, crystallization, and we can add to that list. There's a number of ways of representing enthalpy changes, and one of that is by the use of thermochemical equations. For exothermic reaction, the chemical equation is written and the amount of energy produced is placed on the product side. In this example here, where sulfur is burnt in oxygen to produce sulfur dioxide, that amount of energy is produced and it is shown as a product. So for exothermic changes, the energy produced is written as a product. For endothermic reactions, the chemical equation is written and the amount of energy absorbed is placed as a reactant. So point to note is this, that if a reaction is exothermic in the forward direction, then it is endothermic in that direction. What it means is that, look, when sulfur reacts with oxygen, you get sulfur dioxide and that amount of heat is produced. To reverse this reaction now, we have to insert back that amount of energy into the sulfur dioxide to decompose it to produce sulfur and oxygen. So reversing this reaction, we'll start with what was product here as reactant. So I put the sulfur dioxide here and take that as a reactant now. And what were the reactants here become the product here. That's very easy to do. To reverse this reaction, place these here as products and then make these reactants. Another example of an endothermic change is when gaseous nitrogen react with oxygen to give you nitrogen dioxide. And you can see for that to happen, you need energy. That's why the energy content is placed as a reactant. Of course, reversing this equation makes it become exothermic. All these now are going to become products, and nitrogen dioxide molecules will become reactants. Another way of representing enthalpy changes is by the use of the delta H notation. And the example that we're using here is that of sulfur reacting with oxygen to give you sulfur dioxide. If you go back to that reaction now, we can see that it was an exothermic change. Here you see that we are putting this as a product. When you use the delta H notation, there is no plus sign here. All that is happening, we're putting this at the side of that equation here. So whenever we see a negative sign there, note that it is an exothermic change. Go back to this equation again, as we done previously, using the energy as a product. Here you're not seeing any sign, you just put in a plus sign there and that's the amount of energy produced. Using the delta H notation now, that became negative. So note that. We can reverse this reaction and make it an endothermic change. And like we said before, this will become reactant and these will become products. But see what happens here now. Because we are reversing the reaction, the sign on the delta H value is changed from negative to positive. So note that. Whenever a reaction is reversed, the sign on the delta H value is changed. If it is positive, it is changed to negative. If it was negative, it is changed to positive, as in this case here. This other reaction here again demonstrates that for an endothermic change. Again, the delta H has a positive sign there. If we reverse this now, like we've spoken before, make this reactants and make these your products, then what's going to happen? This sign here must be reversed. There's a little mistake here. This should have been Negative 66.4 kilojoules. Sorry about that, miss. Another way of representing enthalpy changes is the use of enthalpy diagrams. So there are two axes. This one here is indicating the progress of the reaction, and that one there is indicating the gain in potential energy. Again, we'll use the burning of sulfur in oxygen to exemplify how enthalpy diagrams are used to represent the enthalpy change. Here we have in the reactants, and here are the product molecules. So again, sulfur is being burnt in oxygen to give you sulfur dioxide. Because the reaction is exothermic, the change in enthalpy is given as a negative value. One thing to note is this, is that for exothermic reactions, as exemplified by the burning of sulfur, the reactants are said to have high potential energy but low kinetic energy. However, because it's an exothermic change, the heat that is produced is used to raise the kinetic energy of the molecules of sulfur dioxide. But because of the law of conservation of energy, since this system is gaining kinetic energy, it must lose potential energy. That's why they'll be having low potential energy compared to what they had before, what these molecules had. So point to note is this: a loss in potential energy is commensurate with a gain in kinetic energy. And this is shown for this reaction here. Let's look at another reaction here that is said to be endothermic. We are looking at this reaction here that we did before. This is an endothermic reaction. Let's see how that is represented by this enthalpy diagram here. So here are our reactants, nitrogen and oxygen, and that is the enthalpy change produced when these are changed to nitrogen dioxide molecules. That is the amount of energy that must be added to these to create these molecules here. So look what is happening. These molecules had high kinetic energy but low potential energy. But because they're absorbing energy now, they will have high potential energy but low kinetic energy, following the law of conservation of energy. Here we are seeing a gain potential energy is commensurate with a loss in kinetic energy. So note those little points we're making there. So that's how we use enthalpy diagrams to represent enthalpy changes. There is another way of representing enthalpy changes, and that is by showing the molar enthalpy change. So some points to note. The enthalpy change delta H for a chemical or physical change is the energy change that is associated with any mass of substance undergoing a change. For example, when that amount of sulfur is burnt in oxygen, when 0.321 gram of sulfur is burnt in oxygen, 2.97 kilojoules of energy is produced. However, the molar enthalpy of combustion for sulfur will be that when 1 mole of sulfur, which is that mass there, is burnt. Okay? So enthalpy change is for any amount of substance undergoing a change. But the enthalpy change for 1 mole of a substance is what is produced when 1 mole of a substance undergoes a change. And we'll use this example here to calculate the molar enthalpy of combustion for sulfur, so that we can distinguish between delta H and delta H of reaction. So when we're talking about molar enthalpy change, as opposed to enthalpy change, you're going to see this enthalpy change symbol here, but written as a subscript. You're going to see in parentheses whatever change is taking place, and that will indicate to us that, you know what, we are talking about the enthalpy change for 1 mole of that particular reaction there. So let's look at what is happening here. So in this case, we're looking at the molar enthalpy of combustion for sulfur. All right, let's go back to this problem. You have that amount of sulfur producing that amount of energy. Now we want to know how much is produced when 1 mole of sulfur is burned. So the first thing we do is to find number of moles of sulfur. Going back to our little mole triangle here, number of moles equal to mass divided by molar mass. So that's the mass there, divided by its molar mass, and we get that number of mole of sulfur. Since this amount of sulfur being burned gives that amount of energy, then we can find what is it for 1 mole. So the molar enthalpy of reaction here, specifically its combustion, would be equal to whatever your delta H was, okay, which was this, divided by number of moles, which is this in this case here, and it works out to be 297 kilojoules per mole of sulfur being burned. But an important equation must be established. The molar enthalpy change will be equal to the delta H of the reaction divided by number of moles. So that one equation you should hold in mind. This equation here, the molar enthalpy change for any change is equal to the delta H divided by number of moles. Or we can write it like this: the delta H is equal to the delta H of the reaction is equal to the molar enthalpy change times the number of moles. To find the molar enthalpy change for any reaction, if you're given the enthalpy change as was given in that case here, take that and divide by the number of moles involved there as was shown here, and that is equal to the molar enthalpy for combustion of sulfur. And we have established this equation that will become useful later on. Keep those in mind.